Hi folks, welcome to my talk about immutability. I don't have any slides. The closest I've got to slides are text files, because switching between Visual Studio and PowerPoint all the time ends up being really annoying. This is now working, hooray. There we go, brilliant. Thank you, AV folks. All of this code is on GitHub. So go to, well, if you look at all the repositories under Jon Skeet, there aren't that many. So under demo code, there's all the demo code I give for various talks, so you can investigate abusing C# and C#7, all kinds of stuff. This is, in theory, what we'll talk about today. In reality, I've given this talk 5, 6 times. We've never got through it all. I've done different bits each time. So that's another reason to go to the GitHub repository so that you can see all the bits that I didn't get to. I will not be in a discussion zone after this because I'm heading off to the airport. So if you want to talk to me more about it, feel free to come to the airport, and when we're through security, we can discuss it for ages. That would be somewhat extreme devotion to the craft, though. Okay. Oh. An easily pleased crowd, that's what I like. Okay, let's talk about immutability. So the word immutability means something that can't change. However, the idea of a type being immutable or not isn't nearly as simple as it sounds. We have a whole spectrum of mutability, and I'll give you some examples along that spectrum. So let's start off with something that we can all agree is mutable. So here I have a class, and it happens to be sealed, but it's still mutable. We have a value property that you can get and set. And here's just a brief example demonstrating we can create an instance, we can change it, we can observe those changes. Okay? So far, everyone should be happy. This is simple. Now, how about something that is shallow immutable? So this time, we've got 2 properties, both of which are read-only properties. So this is a good start in making something immutable, but one of them is a string builder. I'm sure you all know string builder. You can append to it, you can change the contents of a string builder. It's a mutable type. Unlike string, which is immutable, string builder is mutable. So even though we cannot change, if you imagine the object itself, shallow immutable, we can't change the bits within that object. They will stay the same. However, this object refers to an object over here. So that reference stays the same the whole time, but this object can change. Okay, so you could think of, I like to give the idea of objects being like houses, and references being like a street address, and variables being like a piece of paper. You could have a museum, and the contents of the museum never change. That's like an immutable object. But in that museum, there's a piece of paper giving an address to another house. And that's a party house, it changes all the time. So, the museum itself is not changing, but you can still observe changes to state by observing what you see in the museum. Does that make sense? Okay. So, not very immutable. Next we have what's called, well, what Eric Lippert calls Popsicle Immutability. I don't know whether popsicles happen here in Russia. They're not called popsicles in the UK either, but basically you can buy in the shops little tubes of liquid in clear plastic tubes, as I say, and you take them home and you put them in the freezer. And before you've put them in the freezer, you can bend them. It's all, they can be changed, they can have their shape changed. You then put them in the freezer and later eat them as an ice lolly. So the idea of popsicle immutability is there's a point in time at which we freeze it. We make it stay the same afterwards. So here we have a simple, probably incorrect version of popsicle immutability. So we have a value property, and you can always fetch the value, and that's fine. When you try to set the value, if it is frozen, if the object is frozen, then you're not allowed to do it. You can check whether the object is frozen or not with the frozen property, which only has a private setter, which is set by this freeze method. You can call freeze many times. You can make it frozen, even if it's already frozen. You can't go the other way. You can't thaw this popsicle. So using that, we can set the property twice, freeze it, see the value, and everything that observes the value will always see this value of 15, maybe, if the memory model works for us. I'll talk more about the memory model in a bit. But if you try to set the value again later on, it goes bang. There are times at which this can be appealing. I'll go into some of the pros and cons of it later on. But for the moment, let's just move on to our next. This is one of my favorite examples to talk about. So here we have something that we could call observably immutable. So we have a name property, which is read-only. And it's a string, and I assert that strings are immutable. But we have this non-read-only field that is ignored in equals, that's fine, but in get hash code, it can change. Okay? If it was previously 0, then we'll get the hash code of name and return either the newly computed or the cached version. So, out of interest, how many of you, I know I asked this yesterday, but maybe it'll have changed, how many of you have done some Java? Yep, oh, quite a few. How many of you believe that Java lang string is immutable? Okay, that's a small number. Java lang strings widely believed to be immutable. How many of you would call, if you had to say immutable or not, how many of you would say this class is immutable? Okay, and how many would say it's mutable? Okay, the majority of you won't put your hands up. Okay, so Java lang string is just like this. Okay, it caches its hash code. I don't know whether .NET, I don't know what .NET does in terms of string hash. I think it may compute it every time. I would call this immutable, in that suppose we changed it so that we did read-only int cached hash, and we did cached hash equals name.getHashCode. Suppose we changed it to be like that. Then it genuinely is, clearly everyone's going to agree it's immutable. How could I tell the difference if the previous one was version 1, and this is version 1.1? Can I, from the outside, observe the change here? Well, I could observe it in terms of performance, because this will take longer to initialize, but that's probably it. Even the memory model that I keep on sort of obliquely referring to won't be a problem in this case, because we've got an int, and ints are atomically set and fetched, and even if we've got two different threads and we end up with two threads calling get hash code at the same time, and they both observe it to be 0, so they both recompute it, they'll compute it to the same thing and then write the same value, so we'll never see any discrepancy here. So this is immutable, but might not look that way to start with. And imagine you were trying to write a checker to validate that anything, suppose I had an attribute that I used to assert that this was immutable, and I had some static type checker to check that it was immutable. It would need to know about this pattern. Or I'd need some way of saying, I've validated that it really is. You may not be able to tell, but please believe me, it really is immutable. Okay, from something that looks not immutable, but is, to the opposite. Here is a class with a read-only property of an int. Int is a value type, and immutable anyway. So is this immutable? Well, there's no way of mutating an instance of just unsealed semi-immutable. But if I have a variable of type unsealed semi-immutable, I cannot guarantee that I won't be able to observe any changes in the object that that refers to. Because it could refer to an instance of a derived type. My type isn't sealed, so I can extend it, and here's one with a rewrite property. Now in this case, I've made it obvious by overriding to string here, but even if I didn't have that, you could argue, well, something else later on, a pattern match or whatever, could check that, could react differently to an instance of just the base class versus a derived mutable. So some of the benefits that I'll come to later of immutability don't hold here. So I can't cache a variable of type unsealed semi-immutable and be certain that nothing's going to change it and it's always safe to give out and I can just give it out without any copying or whatever because no one can change it. They might be able to. So here we have an example. We create an instance of derived mutable, and then we have a variable unsealed semi-immutable, which is a reference to the same object that we know as derived mutable, and we can mutate it, and we can observe that mutation, in this case, via toString, but if nothing else, you could always cast. Okay? Happy enough? I'm not getting a lot of feedback here. If anything I'm saying doesn't make sense, it is up to you to shout that it doesn't make sense. I will not be held responsible for not making sense if no one tells me. Okay? Right. So, this is something we've all sort of done. So here is a class, lazily immutable. And lazily, this isn't like lazy of T, that it will compute something later on. Arguably, that's what our observably immutable earlier on was. It was, I've got this value property, and I can set it privately, and that's good enough. It's immutable. But later on, I need to fix a bug, and I just set the property. At which point, it is no longer immutable, because if you call fixBug, it will change state. So often when people were designing immutable types prior to C#6, they would do this because they didn't want to bother writing private read-only int value public int read-only value get return value. Okay, that is more work, but that is really what we want when we lazily put this. The good news is, as of C#6, you don't need to care. You can just do that. Okay, so read-only in C#6, it's all good. I'll come on to the evolution of C# in a bit. So that's being lazy. This is at the other end of the spectrum from our first obviously mutable. This is obviously immutable. You can look at the source code, you can tell it's a sealed class. Nothing can derive from it. If you have a variable of type really obviously mutable that's non-null, it can only refer to an instance of really obviously immutable. And there is nothing we can do to change that after construction. Within construction, we can change this several times. So we can do value equals 30, value equals 40. In fact, sorry, value equals 30, value equals 40. We can be changing it a lot. And if you have something that, say we have an action really obviously immutable action. So this is, I've never talked about this in the talk before. But if you have some kind of callback that gets passed in, and we pass it like this, then even though this is kind of an immutable type, this callback could observe changes. Suppose this callback retains a reference to the object and starts a new thread that prints out the value of value, if you see what I mean, several times, then it could print out 30 and then 40. It would be able to see the changes during construction. So this is why you never do that, basically. Unless you're writing a WinForms app, at which point you're invoking event handlers and subscribing event handlers all over the place, and please do so carefully. So for the rest of the talk, I will ignore the idea of leaking this from a constructor, but it's a dangerous thing to do, don't do it. So one final wrinkle, I showed when something is unsealed, it becomes mutable effectively. What about if it's unsealed, but it only has a private constructor? You may wonder why this is useful, because who can create an instance of this? Well, clearly you can create instances within this class, but why would it be, in this case, this is even abstract. It's not just not sealed, it's abstract with a private constructor. And you can sort of see at the bottom of the screen what's going to happen. If you remember, I'm sure you're all intimately familiar with the access modifier rules of C#. You can access private members within the text, within the program text of the class that declares that member. And a nested class is within the program text of the declaring class. So within derived one, it's fine to call this private base constructor. Okay, this isn't a trick that's abusing C#. This is by design that you can do all of this. And this is a really useful pattern, because it means any instance of unsealed private constructor is actually an instance of derived one or derived two. Both of these are immutable. And the maintainer of unsealed private constructor can fairly easily verify the whole of the program text of unsealed private constructor and check that all the private derived classes are immutable. If you had any public classes, if this were public there, that's now a problem, because someone else could derive another class from derived one. I could make it public sealed, at which point it's less of a problem. It's all, it gets quite hairy, all the possible options. But this is really useful if you've got inheritance of, say you're modeling mathematical operators. So you could have the addition operator, the subtraction operator, the division operator, and the multiplication operator. And for whatever reason, you want to use an abstract class rather than an interface. And apart from anything else, this pattern means you can guarantee it will always be one of those four types, which can be useful. It's not as extensible, but it can be useful to have constrained things. You can have factory methods, all kinds of things. Useful pattern, particularly with immutability. Okay, so those are some of the aspects of the immutability spectrum. I've told you what it is, but not why we want it. So, I mentioned yesterday in the keynote the worst bits of Java, the Java standard library. There are quite a few bad bits. And .NET is generally a lot better, but Java util date and Java util calendar are appalling. And Java util date we'll concentrate on because it's a lot simpler. Despite its name, a Java util date isn't a date, it's an instant in time. And it's mutable. So a date feels like a natural value. Okay, they modeled this correctly for integer, Java lang integer, a boxed int, basically, you can't change. They recognize it's useful for that to be immutable. But a Java util date is mutable. So what does that mean in terms of, it's quite common, very common, to want to have a field within your type that is a Java util date. And maybe it's still a mutable class, but generally you want to have control and be able to reason about when the state of your object changes. Okay, so imagine the museum idea again. So imagine our museum is no longer immutable, it's a mutable type, but typically museums don't allow their visitors to take stuff out of the museum or put extra bits in. Okay, it's only the curators of the museum who are allowed to change it. Okay, I'm not sure how well this analogy is going to work. This is the first time I've used it sort of off the top of my head, but it's working fine so far. So if you imagine the curators are the code within the museum type, they can control how the mutability works. So suppose we have two dates, a start and an end. Okay, we're modeling an interval over which some time happens. And we allow a user to start recording and stop recording. So start, we'll change the start time and maybe clear the end time, set the reference to null. I'm not one of those people who think that null is the worst thing ever. It has its uses. It can be annoying, but it has its uses. So suppose we have a maybe of date, whatever it is. And then when we end the recording, we set the end point, and we can check that it is later than the start point. That's great, but it means you can never return that Java util date to a caller. Now, a caller may well want to know, when did this thing that you recorded start, and when did it end? And we have maintained the invariant that when there are both start and end, start must come before end, because it doesn't make sense to start recording something and finish earlier than you started. Well, if you model this, I don't have any Java code here, but if we have a public class museum, and we have a private date start, private date end, public date get start, return start. Okay, that code is broken because, say we have this. So obviously we've got the begin and end recording as well. And you know, I do have some control over things. I'm not allowing the user to call set start, but that doesn't really matter because I can call set get museum new museum. Museum.getStart .setTime minus 1,000, or yeah, 1,000 and well, hey, we have gone backwards in time. Okay, this has broken any control that the curators have over the museum. Their invariant has been broken. This is a good example of why datetime is an immutable struct in .NET, because it makes sense. Instead, to do this properly, you'd have to do new date start, or start.getTime. I can't remember exactly what you'd need to do, but you'd need to construct a whole new object to give to your caller. How often do you think the caller is actually going to do the wrong thing and be trying to break you? Probably almost never. But if you want to make sure that you can always reason about your own code, you want to make that absolutely never. So imagine that you then have a constructor, public museum. We can't just do this.start equals start. No, allowing the caller to pass something in is just as bad, because they could do new museum start. Right, now you've validated your invariants, I will screw things over, I will set the time to be whatever I wanted it to be. So no, you've got to do new date start.getTime. So at that point, we're constructing date objects all over the place. So being immutable means that you create fewer objects, right? Yeah, not at all. It means you create fewer objects in some cases. In other cases, it means you create far more objects, because you can't change them. So if you want to observe an instance of the museum at one point in time and an instance of the museum with different values, if everything is genuinely immutable, then you would need two different instances of museum. And every time you make a change, that has to be creating a new instance of the type. So if anyone starts telling you immutability means you have to create more objects, you can give them that date example, saying, no, it means that I would be able to give callers a reference to an object because I know they can't change it. And if anyone says the reverse and says immutability means you always create fewer objects, you can say, well, no, it means I can share things, but anytime I want to be effectively changing state, then I have to create new instances. So it's not a one-size-fits-all type of thing, you need to understand the pros and cons. However, the pro of being able to understand your code is definitely a big deal. I will just a brief thing about mutable structs. We have structs in C#. The typical advice is you make your structs read-only, and you don't include any reference types that are, sorry, you make them immutable and properly immutable, so you don't put a string builder reference within a struct, because then we have the same problems of shallow immutability that we had earlier on. Mutable structs behave particularly weirdly when they're boxed, particularly if they implement an interface, then you can have things where you kind of can't change things badly while they're a struct, but as soon as they're boxed and you can refer to them by the interface, then you can mutate them in place and other people will see them. Broadly speaking, just say no. Since I first gave this talk, C# 7 has come out. How many of you know enough about C# 7 to know about value tuple? A few. Quite a few. This is good. Let me show you roughly what value tuple of T1, T2 looks like. That's kind of what value tuple looks like. It's got a load more members and stuff, but it has public mutable fields. This scared the heck out of me when I first saw it. The way to think about value tuple is it's just a bag of variables. Certainly when you have a variable, it's a bag of variables. If you're passing it as a value, it's a bag of values. And the reason that after a while I learned to live with this is there's no attempt at encapsulation here. There can be no invariant saying item 1 must be less than item 2 or something like that. Value tuple has no idea of what these values are meant to mean. Whereas for most structs, you do have some kind of invariant or you're attaching meaning to the various fields. So it makes more sense that you're constraining what you can do with them. Here, really doesn't matter. So value tuple sounds like it goes against all the guidelines, but it's for a reason. Do not be fooled into thinking that means the guidelines were wrong. It just means that you need to understand why they can be applied and when they can be applied. You will almost certainly, particularly as value tuple now exists, you will almost certainly not need to create your own mutable value types. Use tuples instead. Okay, so that's kind of why we would want immutability. I will briefly, let's see, right, we're halfway through. What did we get in C# over the different versions? So C# has always had value types. This is good, yay. We have string and string builder. This is good. This is so far kind of so like Java, except Java doesn't have custom value types. It's only tangentially related to immutability, but I have always wished that C# classes were sealed by default. And out of interest, and I'm going to ask you both ways because I know most of you won't put your hand up. Please, have an opinion, damn it. Right, how many of you like the way C# is and are glad that you have to say when to seal a class? Okay. How many of you would rather C# had sealed by default? This is interesting. This is now just a bit more having my opinion, and I hope this isn't just politeness. Never be polite to me, okay? If you disagree with me, say so. I'm probably wrong. In this case, I'm not, but So I used to go to conferences and things and talk with people, and I was always in the minority. And people were saying, no, never seal your classes. It means it's awful for testability. And I have met a few people who over time have come back and said, do you know what? Yeah, all those times that we thought we'd want to be able to change things and want to be able to mock stuff out, it turns out there are better ways of doing things. And yeah, seal your classes. It shouldn't make a difference. So C# has methods being non-virtual by default. Java has methods being virtual by default. That should make no difference. Okay, if we were all diligent and we designed things in Java the same way as in C# around inheritance, and they're very similar on that front, then you would expect roughly the same proportion of methods to be virtual in Java and C#, right? No, not at all. I would say that in C#, the C# that I see, maybe 5% or 10% of methods are virtual. And in the Java that I see, about 5 to 10% of the methods are final. This is the power of defaults. So, as a designer of languages or APIs or whatever, you often have three choices. Default to one way, default to another, or force the user to express an opinion. Going back to Noda time, I like to make people think about what they want and then make it easy for them to tell me what they think. So I go for the, you must tell me how you want to do something. I will give you two easy options and then a custom option, but you have to decide. Okay, diversion over. C#2, finally, and this was weird in C#1. You couldn't have a public property that was publicly read-only but privately writable. You could have just read-only or just write-only, but they had to, if it was read-write, they had to have the same access modifiers. Okay, that feels, however many years later, really weird, and it was clearly a mistake, so they fixed it in C#2. This is the only time that you ever need to write private in order to accomplish what you want. Because by default, C# will make the default access modifier the most private it can be for any scenario. So a field declared in a class is private by default. A class itself is internal by default, unless it's a nested class, in which case it's private by default. That kind of thing. However, by default, that's just public. You have to explicitly say, no, I'm changing things. Right, C#3 gave us anonymous types, which are shallow immutable by default. In fact, in C#, they're always shallow immutable. In VB, you have to use the key property, or the key modifier, to say which properties you want to be immutable, and those are the only ones used by equals and get hash code. I think this was a mistake, but I'm not a VB programmer, and maybe it works exactly as VB programmers expect. But I'm glad that C# went the way it did. Link itself didn't enforce immutability, it just strongly encouraged it. If you see people with a select method that, I sometimes see things like this. List.select x goes to x.name equals changed, x.value equals 10, whatever, and then, oh, do you know what, I'll just count it. Not use the count afterwards, but I want it to force this to evaluate everything because I want to apply this action to everything. Don't do that, and if you have colleagues who do that, tell them not to, and tell them that Jon said not to. It's a horrible abuse of link. It works, it's predictable, it works. I'm not going to say that it doesn't, but it's not the way it was designed. Okay, we have object and collection initializers. So, just in case you have forgotten, new person, name equals Fred, friends equals, things in there that are added to the list of friends. So, this is sort of nice, but it encourages mutability because they just don't work with immutable types. It has to construct the person, then set the properties, or then call add on the properties. It's really, really nice for working with already mutable things, but it does encourage mutability. So that's saying what I was talking about. With C#4, you could argue that there's nothing in C#4 that gives you more immutability, but it does mean that when you call a constructor, with lots of parameters, you can specify named arguments, which makes it much clearer. So if we had message box XY, imagine message box is immutable. I have no idea what X and Y mean. Which is the title, which is the content of the text box, the message box. Here, it doesn't matter even if I've got them the wrong way round, because I can just specify. So that's a good thing for immutable types are now easier to use because of that. There's nothing in C#5 around immutability. There's async, and async's awesome, but there's nothing around immutability. C#6 finally has read-only automatically implemented properties. Hooray! It only took 10 years. You can now write default values, so you can write initializers, public int value get equals 10, and that works for mutable ones as well. This is particularly important. Imagine you're going for shallow immutability, so I can have a list of friends, new list of friends. Then you can give a default collection, really useful. Anyone can then mutate that list of friends, but they can't change which list the property refers to. Immutability is great, but don't feel you have to go all the way all the time. And finally, on a psychological level, expression body members. Everyone know what I mean by expression body members? It's when you write, public void foo, and then instead of braces, you go bar times 5. This doesn't make anything any more immutable than it was before, but it makes you feel like an F# programmer. So suddenly, your IQ goes up by 10 points, and everything's immutable. I'm only half joking. Obviously, I am joking. It doesn't give you any more IQ points, but it encourages you to think in a more functional way, which means you're more likely to design things immutably, I think. It certainly makes me feel that way, and I was surprised by that, and I love them. C#7 has come out since I last looked at this slide deck properly. You can tell the level of diligence of preparation I perform. Value tuple, mutable, struct with public fields. Arg. Oh, all right then. Yeah. So, we get used to it. As I say, I now think value tuple is a wonderful thing, but I didn't before. Nothing else. C#8, who knows? Okay, there are thoughts around C#8. We may finally get record types. Record types were going to appear in C#6, and then they decided not to. If you really liked the record types that were going to be in C#6 and were disappointed when they were taken out, I apologize. I may or may not have had some effect on that, because I wrote a blog post saying, they kind of look nice, but they wouldn't work for me. And that was meant to be only, they wouldn't work for me. I have some problems with them. It was announced shortly after that they were coming out of C#6. I don't know how much that's correlation or causation. I know the C# folks well, and I know that for better or worse, they value my opinion. I don't think I've got quite that much influence. But I think they did the right thing by waiting, and they're trying to put multiple things together at the same time. Right, I now have 20 minutes. 20 minutes isn't too bad. Okay, so we're going to look at some examples of how you can do immutability, which may have been the sole reason you came for this talk and you've been kind of asleep for the last 40 minutes. Now's the time to wake up. So, a basic data model. We're trying to model a person with a name, an address, and some phone numbers. So that's a collection. We're not going to get to friends. Let's not worry about that. So an address has a street and a city, because modeling more than that gets complicated. And frankly, modeling addresses in any kind of global way is... likewise, a phone number, it's just a string for the moment. There are better ways of representing it. I'm lazy. And we have a type for the phone number, which can be home, mobile, or work. And suppose we have decided we want to make this immutable, or have some immutable representation. This example came from the protocol buffers example. Protobuf is Google's serialization format. We use it all over the place, and it's public and open source. And back in 2009 or something, I ported the Java version of Protobuf to C#, and that uses the builder pattern that we'll come to later, and is immutable everywhere. A couple of years ago, I rewrote the Protobuf implementation for Proto 3 that we use heavily in gRPC and our cloud APIs and things, and I decided, despite all the benefits of immutability, it's all mutable. I decided that having looked at all the different things that we'll see here, none of it hits the usability bar that I need for types that I'm going to expect people to work with. We'll see how far we can get. The records in C#8 may well make all of this, may make me revisit Protobuf and have an option for generate C#8 record types instead of the others. Okay, so let's give some examples. Let's start with the builder pattern. So, we're using the Immutable Collections, which if you haven't used, I encourage you to do so. I believe they're part of Net Core, but not Net Standard, because they're not part of .NET 4.6.1. But you can easily use them from NuGet, and they are just properly immutable collections with various ways of building them. So, here we have person. It has these things. If we believe that name, that the string is immutable, that's good. Address is immutable, because we're doing that separately. Immutable list is immutable, and importantly, phone number is immutable as well. So it's fine to have an immutable list of mutable things. Imagine this was string builder. Well, that's kind of our shallow immutability, but one level down. So yes, I can't change the list, but I can change every entry within the list. So if it's anything non-empty, then it's effectively mutable. So those are the only properties. There are no separate fields, so we can say this is immutable. How do we create one? Well, you don't call a constructor. The only constructor is private. Instead, you create a builder, and this is fully mutable. So we have a name that we can get and set, an address that we can get and set. Note that we are still using the immutable type here. And phones, well, you can't change it to a different list of phones, but you can add to the list. It's just a normal mutable list. Optional, public void set address, address.builder. This doesn't work terribly nicely with C# properties, although you could have address.builder, address builder. But then, what do you do in here? You could set address to the immutable version of the builder that you're setting and create a builder from things. It becomes hard to reason about. Okay, this is a big deal, is what can I reason about? And anytime that anything is itself immutable, it's easy to reason. As soon as you get to the, well, I'm dealing with a mixture of mutable and immutable types, it becomes harder to reason with. So, address looks very similar. You know, we have the builder, and we have a build method that just constructs itself by passing the builder to the private constructor that then copies everything out. And in person, when we copied everything out, we created an immutable list from phones. We would do nullity checks to make sure that the name wasn't null and that none of the entries in the phones are null. That's all sort of by the by. We use this like this. And this is why it's not nice. Okay? Let me just show you something that won't compile. But if we had a mutable version, we wouldn't need the builder there. We wouldn't need that there. We wouldn't need build. We wouldn't need .builder. We wouldn't need build. Okay? So this is what it would look like in Proto 3. But with mutability, you've got this, the builder pattern is everywhere. It's really hard to ignore, which is sort of good, because if it's in your face, you can't accidentally think, I was using the wrong thing, but it's not code that you want to use. Mutable, it's code that you want to use so long as you don't need to maintain this object for a long time across various things. We tend to use protobuf in RPCs, and you create a request, you send the request, you get a response, you do something with the response. You don't keep a request around for a long time, you don't keep a response around for a long time. You probably convert it into some other model. In that sense, mutability is fine. Unless you maybe want to have the same request that you send, you're polling something periodically. If you're going to reuse that request, you need to be careful not to mutate it. You see how it's definitely a pros and cons issue. If only computer science and programming were full of golden rules that you could always just follow and you'd be fine. It isn't. Okay, so that's the regular builder pattern, and that's the one that's implemented. If any of you have used Google.protocol buffers, which is the Proto 2 one, as opposed to Google.protobuf, which is the Proto 3 one. Sorry. Naming's hard. That's what you'll see. Or you might see this version. So this has a very similar public API, in that you create a builder and you can set properties, and you can get a list of phones, which is just an iList, and you can add to it. But look at what happens when you set a property. Turns out person isn't really immutable. It's only observably immutable. Internally, the builder creates an instance of person and then mutates that directly. So instead of several fields, imagine this is a big request with lots of fields. Instead of in our builder 1, where we have several fields in the builder, so you create a builder object, which is big because it's got lots of fields, and then that has to create a person object, which is also big because it's got lots of fields, and it has to copy everything down. Our second one, the builder just creates an instance of person and then pokes at it. And it's the builder's job never to show you that person until it has sort of frozen it. So this is like our Popsicle Immutability. So you poke around, and then you call build, and it says, here is your person. You won't observe any changes to it. Nothing can change it now. And we say, we clear our underlying field, because it would be awful if you could create a person.builder, poke at it, call build, poke at the builder a bit more, and that changed the one that you've already released, as it were. And this comes back to what I showed you earlier about letting this escape from a constructor. Don't do it, just like if you're trying to do this kind of model, you need to be careful not to poke things after you've said that it's going to be immutable. I wouldn't recommend doing this because it's a memory model nightmare. You might get away with it, or people might observe changes. So if you have two threads poking at the same builder, and one thread calls build, it's possible that with the vagaries of the memory model, the second thread that's poking at the builder might end up poking at the original person. So thread 1 could look at the name, it says Fred, look at the name again, and it says Bill. It's like, this is meant to be immutable. How can this possibly be? And in this case, it's not the fault of the memory model itself, it's the fault of we're not trying to address the memory model in this code. So I think this is how my Proto 2 implementation worked, so don't use it across multiple threads. If you only provide the reference to a person to multiple threads after you've constructed it, it's okay. But never share a builder between multiple threads And I think that's okay. And there are various things that will be similar. Don't share a string builder across multiple threads. String builder is such a key thing in the CLR that maybe they fixed it so that you won't observe changes in string, because that would be really bad. But in general, sharing mutable types across threads, bad news. Sharing immutable types across multiple threads, absolutely fine, because they can't change each other's state. I'm sure if you've been to any talks about threading, they will have said, the speaker will have said, the key problem in multi-threading is shared mutable state. Shared state is fine if it's immutable. Mutable state is fine if it's not shared. Put the two together, bang. Just don't do it. Or if you've got to do it, be really, really, really careful. How am I doing on time? 9 minutes. Okay. Let's look at Builder 3. Right, Builder 3 is a reverse. So we had, in all our builders, we've got a mutable type and an immutable type. In the builder pattern that I've shown, the person.builder is the immutable type, is the mutable type, and person is the immutable one. Here, we've got the reverse. So person is your builder, and then you can call to immutable. And this is sort of immutability when I want it, but it de-emphasizes immutability, and chances are everyone else is going to use the mutable one all over the place, and if you insist on the immutable one, you'll be the odd one out. No one will use your API. You will sit by a river and cry. It will be sad. So this is a good idea. It sounds okay, but it comes back to people just use the defaults. They will not use your nested type unless you force them to. With the builder pattern, you do force them to, because you can't create a person on its own. Here, you can create a person, you can pass a person around, and everyone's happy until someone makes a mistake and mutates it, and then they sit down by the river and cry. So, Builder 3, everyone cries, basically. I will briefly show you record. So this is code that won't compile. So this would be what it might look like in C#8. And yep, nothing compiles. It took a very long time for Roslyn to realize that I was making stuff up. This is what it might look like in C#8. And this is all the code, apart from the phone number type enum. So we have less code for all three types here than we have for just the person in the builder pattern. Wow. And the idea is that the C# compiler will then allow us to modify these immutable objects with withers. I'll come back to how we can implement withers at the moment. But basically, you say, I want an object that looks just like that one, except for these changes. And we do this with a new with contextual keyword, and you say, someone else is the same as this object, but with these changes. And that will be lovely, assuming that happens. For the moment, if you want to do something similar, you can create, here is an implementation without a builder. So everything is immutable. In order to construct a person, you have to provide everything at the moment, although anything can be null. So you can do new person, null, null, null. But then you can call with name, and then provide a name. And with address, and provide an address. And with phones, and provide a phones. The downside of this pattern is if you want to mutate in 10 different ways, you have to call with 10 times, which creates 10 new objects. And each of those objects is going to have at least 10 fields, because we're mutating 10 times. I call these pseudo-mutators, by the way. It's a very nice pattern to have available, and consider this pattern in other domains where you're going from one type to another. So in NodeTime, I have local date time dot in zone, and then you provide the zone and say how you want the conversion to happen. And you can do all kinds of things, chaining to convert from one type to another, and that works perfectly well with immutability. When you're doing it within the same type, so this local date, but with a different calendar system, that works fine, but you can have an n² impact on your memory allocation and computation. And the garbage collector is good, but it's not free. The benefit of records in C#8 is, imagine I've written with phones equals, and then done something. I don't know how we'll be able to modify. One of the difficulties with withers is, well, I don't want to modify John, but I want to modify the phone number that's the third in the list. And one of the difficulties with immutability is, if you modify something down there, that means you've got to have a new list, which means you've got to have a new person. And aside from the performance issue of that, just building it up can be painful. There's an idea of lenses, which I haven't looked at, but I've heard about. Go ahead and research it yourself. The good news is I don't have time to put it into this presentation, so I kind of haven't felt the impulse to do so. But withers in record types allow you to specify multiple things that you're changing, and it will only create one new object and do all the changes that are required to do that one change, because you don't want to have to specify all the old stuff in your code, but the compiler's perfectly happy to do it for you. So it's putting grunt work into the compiler. Right, we have about 3 minutes. I think that's all the demos that I wanted to show. So let's go back to the pseudo slides, as it were. I'm going to talk very briefly about why immutability is hard, and then I'll wrap up. So cycles can be hard if you have two immutable objects which refer to each other. You can't build that in a nice, obvious, safe way. You can build one of them with nothing, and then build one of these that refers to that, and then a new one that is that, but with a reference back to it. So you could create two objects, or you could break the rule that I said before about letting this escape in a constructor. So you could build this one and say, I would like to build another one of these with a reference to this. I promise not to mutate anything afterwards or something. So cycles are hard. Fundamentally, one of the reasons we have difficulty thinking about immutability in our type system is inheritance is all about adding functionality. So there is an interface in .NET of iRead-only list, which does not do what it says. It does not say the implementation of this object, the implementation class, is a read-only list. It says this interface only lets you read from it. It's limiting what the interface can do, not what the implementing class can do. Because that would have to be a negative thing. That would have to be an interface saying, you cannot have these members, rather than you must have these members. Okay, so this is built into our ideas of object orientation, are the idea of permitting people to do more things, not saying, we cannot allow this. And immutability is all about not allowing things. I'm now out of time, so I will have time. Come and grab me as I walk if you have quick questions. I'm going to the speaker room and then to the front to have a taxi. I hope this has been useful. There is much more in the slides and whatever if you look on GitHub. Again, let me just put the URL up. You've all been very quiet, but I'm used to that for this talk because there's a lot to take in. Don't feel bad if you find immutability hard. It is hard. It's not easy to design APIs that are easy to use and immutable and perform well. So don't feel bad if you find that hard too. But I hope this has been useful for furthering your thoughts and provoking you to think more about immutability in the future. Thank you very much.